Hello, other people. We are having a math class. Period 9, say hi. Hi. All right. Please, good. Please take out this worksheet, people at home, called Integral as Net Change. And it is coming around right now. All right, so everything we're about to do is good. Everything we are about to do is in some ways like not really new. And it is sort of, some of you are going to look at me like, dude, this is just obvious. If it's obvious to you, great. We are still sort of like milking the fundamental theorem of calculus to like gain deep insights. And what we have done over the past month is to use the problem of finding the change in position given a velocity versus time curve as inspiration to pose the area problem. And we solved the area problem by inventing the concept of an integral, and we learned how to like do integrals by the FTC. But integration is used for far more than just finding, bless you, change in position. It can be used to find the net change for any rate problem. And so let's go. Sometimes people even phrase this as like the net change theorem, but it's not really a theorem in the traditional sense that you like prove it. It's more of just like a principle. Okay, take number 1 for example, which is extremely wordy. Let's read it together. I shall read. Let V be the volume of water in gallons in a reservoir at time t. T measured in hours. Okay, and the idea of like a reservoir is that sometimes the reservoir fills up because like the river or whatever flows into it, or like rains or something, and sometimes it goes down because people are thirsty and take showers. So it is changing. The amount of water in the reservoir is changing over time. All right, well, we can talk about the derivative of this volume with respect to time. And as it says on the paper, V prime of t is the rate of change of the volume of water at time t. In other words, if the derivative is positive, then it means that more water is flowing into the reservoir than is flowing out at a certain time. And the derivative measures the rate at which water is flowing out, the sort of overall rate, because some's leaving and some is entering. And if the velocity, if the derivative of V is negative, more water is flowing out than is flowing in. Okay, so what does, in words, the integral from t1 to t2 of the derivative of the amount of volume the volume represent? What is this? All the people know it? It's how much more water there is in the reservoir at time t versus t1, yeah. Or you might even say it is, well, there's several different ways, so that's good. I'll ask you, are you going to say something different or the same?
Yeah, it's more or less the same, but also I have a question.
Wait, no question yet. So one answer to this is, dude, even if you had no idea what these variables represented, you could just immediately give the answer to this problem. What is the answer to this problem? V of t2 minus V of t1. That is literally what the fundamental theorem of calculus, the part 2, the useful part, says, right? It says that if you take the integral of the rate of change of something, then it is just the change in that thing, right? And also it sort of makes sense that this would be the case. Imagine that we were to make a graph. Here's T1 and here's T2, and let this be V prime. So not the amount of water in the tank, but the rate at which the water in the tank is changing. Well, let's just say that it's something like that. It looks like something like that. Well, then that would mean, well, what does it mean? Then if V prime is positive, it means that V is increasing, which means more water is flowing in than is flowing out, yeah? And if we were to partition this up into subintervals and take a little subinterval here and sort of draw this rectangle, this is now a geometric interpretation of this problem, then what is the meaning of the area of this rectangle in words?
Like how much water came in on that?
Yeah. Just like we did with the velocity versus time, we can also do this for any change versus time. What we have here on the horizontal axis is this tiny time interval, and what we have here on the vertical axis is the rate of change of the volume. And so what this says is, if I multiply the rate at which the volume is changing, which is the height, times the width of the rectangle, which is the amount of time that's gone by, then it makes sense to you that the area of this rectangle is the change in the amount of the water over that small time interval. Follow? And if we just keep doing this, then this second rectangle is the amount of water that we gained over this second very small time interval, because we're again multiplying a rate by like a time that's gone by, and then blah blah blah. And then when the function gets negative, well then what does it mean intuitively for the v prime to be negative? That more water is flowing out than is flowing in. But again, for the exact same reason, I'm multiplying that negative rate by a small time interval, so that gives me the change in the amount of water over that small time interval, and that change will be negative. And so I sort of intuitively want to subtract the negative ones. So it all works out, and what we get is, in words, you know, the net change in the amount of water in the reservoir, or maybe I should say the volume of water, same thing. The net change in the volume of water in the reservoir from time t1 to t2. Cool? Does this strike you as kind of common sense, or is it helpful to like talk it all out, like the meaning? I don't know, both. All right, good. Do the rest of the page. Go. Okay, now your question. Yes.
Well, what? Like it doesn't ever specify the time unit. So it's just gallons per something.
No, I think it does. I think it says hours. Yep.
Oh, it does. I was thinking.
Yeah. So this is in gallons of water.
What gallon of power
The gallon per hour.
All right, so the second one, this is just the same old, right? This is the problem that inspired us to start integrating in the first place. What is the meaning of the integral from t1 to t2 of velocity? Answer? Yup, change in position on the time interval t1, t2. But is everyone seeing now how integration is applicable to all kinds of situations? Anytime you know the rate at which something is changing, if you take the integral of that rate, then you get the overall change. The rate of growth of a child in pounds per year. Alright, so this is time in years. This is the rate of growth, which I happen to know kind of goes down. In those years before puberty, you don't grow that much. But it's still positive because people are growing, man. you know, 10-year-olds weigh more than 5-year-olds. So this is W prime, pounds per year. And again, okay, if you're like a lazy thinker, then you're just like, oh, you know, just thinking, whatever. Nah, man, you should be able, you should at least put a second or two into thinking about why this all makes sense. And the answer is it totally makes sense. Because if you split this up into a bunch of little pieces, then any one of these rectangles has a meaning. If this is like from 5 to 6, then the area of this rectangle, we're multiplying the rate at which the child is growing, pounds per year, times like the amount of years that went by, which is 1. And so what you get is, the meaning of this rectangle is the pounds gained in year 5. Oh, pounds gained in year 6, pounds gained in year 7. I might have done my counting wrong. Anyway, so the overall thing is just going to be the total change in weight from year 10 to year 5. Agreed?
Yeah.
Whoa. Good. How about number 4? What do you got? Everyone seems like done. Total oil leaked. Yup. From the first, in the first 2 hours. Good. 5 has like a small little twist to it. Do 5 if you haven't already. Talk about it with your table.
I think it's
Wait, but here you have to write an integral, right?
You're supposed to use a calculator.
Someone move the camera to make sure we're in frame.
Write an expression.
Okay, honeybee population starts with 100 bees and increases at the rate of n of t bees per week. So notice that I am defining this function to be already a rate function. So this is the rate of increase of bees, and the units are bees per week. Okay, I want to know how many bees there are after 15 weeks. What do you got? Yeah, where's that 100 though? Inside the integral or not? No, it does matter.
Why? Because you can just split it up.
No. Okay, wait, so here a small amount of thinking is required. If I want to know the amount of honeybees after 15 weeks, is it just the integral from 0 to 15 of n of t dt? No. Like almost. What is the integral? What is the meaning of the integral from 0 to 15 of n of t dt?
It's the net change.
It's the change in the number of bees from time 0 to time t equals 15 weeks. Yeah? But then there is this extra little fact, which is that there was an initial condition of 100. And so the answer to this problem is that the number of bees after 15 weeks is 100 plus the change in the number of bees. Follow? Okay, good. All right, the back is one of those things that I usually, let's do it. It's fun. It's hard. Go.
Centerville is an actual place. Yeah, so we better do like stop it like 10 minutes if you get on if you go on that sketch.
Start thinking.
Even knows who you are. Yeah, you just have to take like
You're not a friend.
it's just like
So weird. I mean, sorry. Thank you. Yeah.
I know this is probably
All right, so This entire problem was written as this is called catch a student who's not thinking too deeply about what's going on. What is your temptation? Like, should we talk this problem out for a minute? Has everyone had a chance to read it and put a minute or two of effort into it? You want another minute? Take another minute. That's something like graph because I'm a math teacher.
Gold is I don't know. The world is just
All right, good. Coming back together. Certain math facts shall be used up. Good. Paying attention. Good. The function root r plus 1 is just like the square root function. Move 1 to the left. Agree? So now we need to reciprocate that and then multiply by 6. So I think it is worth it to try to make a picture of this. That will be like a vertical asymptote at r equals -1, although that's irrelevant for our purposes. Well, this graph's going to come down and it's going to be all here up here at 6, and then it's going to look like that. That's pretty much all you need to know. Cool? Okay, what is this graph? It is a graph of population density in thousands of people per square mile at a point r miles from the city center. So there's some city, the center of the city, the population density is high. In fact, what is the population density at the center of the city?
6,000 people per square mile.
6,000 people per square mile, or we could just say 6, yeah. And then, as often happens, the farther away from the center you get, the population density goes down, yeah? And so we have a function. All right, so the sort of units of this graph are, this is population density, and in thousands of people per square mile, and this is miles from the center of the city. All right, and the goal is, number 1. There is some congressional district which covers all people living between 3 and 4 miles from the city center. Find the population of people living in that region. Okay. The ultimate lazy person's way of doing calculus is to be I don't know, just take an integral, I guess. People say that, and those people are bad people. If we try to just draw this graph, and if you don't actually think about what you're doing at all, you might be tempted to think, does anyone just do this? That it's just going to be the integral from 3 to 4 of the population density? I mean, at least one person confirmed. Just yeah, good. The reason why is because, I don't know, analogy of previous problems or something like that. But if you start to think about this a little bit more, that makes no sense at all. Someone talk it out. Yeah, Oscar.
Well, it's because you can't subtract circle. It's start there thingy.
All right, that was incoherent. Ethan.
Population density varies. It's not constant throughout the whole 3 to 4 miles. So you can't just figure out the area and then figure out the number of the density and then put them together to get a nice neat number.
Yeah, the thinking has to come first. You have to actually think about what you are doing. Integration is a process of adding up an infinite number of really small things. You need to know what those things are that you're trying to add up first. Then integration will help you solve your problem. But if you don't even know what your problem is, integrals are not going to help you. What is our problem here? We want to know population, right? But if you think about what this, maybe it's not worth it spending time talking about what's the wrong answer. But I do think some people would, well, at least a couple people thought to do this. If you look at this rectangle and try to discuss what this rectangle means, you start to realize it doesn't mean anything, right? The height of it is the population density in thousands of people per square mile, and you're multiplying it by miles? That doesn't make any sense. Okay, back to the drawing board. Wait, the entire point of this problem is, will become clear in a minute when we finish it, that taking the integral is the last thing you do. Thinking, understanding, deciding what it is you are trying to add up is like the hard part. Once you have something that you're trying to add up, then just add up smaller and smaller pieces of them, and then you have a Riemann sum, and then you have an integral. So resist the temptation to just be like, oh, it's just an integral. All right, so someone make a suggestion, or go back to the drawing board for 2 more minutes. You got a suggestion?
Yeah, take the average value, and then that's like the average population density per square mile, and then you just like multiply by 1.
All right, now we got a suggestion. He says, aha. He says, look, so that we care about all the people who are living between 3 and 4 miles away. Well, what is the population density when you are 3 miles away?
3.
I think it is, in fact, 3, right? Because I just plugged 3 in here. And if you plug in 4, what do you get?
6 over root 5 over 5.
So like kind of a little bit of a gross number, right? Yeah, 6 over root 5. All right, and so now he says, let's take the average, but not the average of those 2 numbers. He's more sophisticated than that. He says, let's take the average value of the population density function. So now I'll know how far people live in that congressional district. We'll know the average population density, and then do what? What's that information?
Multiply by 1 because it's like 1 mile.
Multiply it by 7 pi miles squared because that is the area of the district.
7 pi miles squared. What are you talking about? Can you explain?
Well, it's circles, right? So
Circles, yeah.
there's a circle of radius 3. That's the distance you start away from the city. And then you go up into a circle of radius 4. That's where you stop. So 16 pi of the big circle minus...
Yeah, wait, hold on. Give me a second to catch up.
Okay.
Also, have you guys heard the news that some freshman finally made a polar machine?
Yeah.
You heard the news?
Yes, I was there when he was in.
Yeah. Oh, yeah.
Wait, what?
I don't know who this freshman is, but he is my new favorite student. I've never met him.
And wait, what did you make?
You'll see. I'll bring it in one day. We'll
It's
do
like a
something.
wooden thing with holes.
All right, so yes, if this is city center, Colin's saying, hey, we should make like a picture of like what the hell is even going on. What is this congressional district? It's all the people living in this like ring that's like between 3 and 4 miles away from the city. Agreed?
Yeah, that's gerrymandered.
Okay, what?
That's gerrymandered.
You can't have a congressional
Good.
district.
Good. Wait. Good. Hold on. Wait. No. Good. So now, if you combine Carlos's idea with your idea, have we solved this problem? We just take the average population density on the interval 3, 4 and multiply it by the area of the congressional district. All right. Finally, we have an answer which is coherent because we are multiplying population density, which after all means people per square mile. Is everyone following this? Times the number of square miles of the district, and that will give me population. It is coherent, but is it correct, Bumjin?
I feel like it's overgeneralizing, and if you have like extremes, then it'll be like a weird answer that won't really work out. So like, if you have...
Please elaborate. So you think that this is wrong?
Yeah.
Okay, explain.
I feel like average isn't specific enough to really get a good answer.
Yeah, I want you to continue explaining why. This is like a little bit subtle. Why is the Carlos-Collin method doesn't quite work? And by doesn't quite work, I mean it's wrong. Max.
Because there's more of the outer ones.
Okay, you go on the right track. Can you articulate that a little bit better?
So like the farther out you get, the more of that density there is, because the circle's bigger.
Sam Schulman, yeah, that was pretty good.
Yeah, I was just thinking it's kind of like when we were looking at how average value doesn't quite work. The example we used was temperature, how like a temperature can kind of change through a day.
Yeah.
And average values doesn't quite get the accuracy we want.
Okay, yeah, I think what Max was saying was a little bit more specific. What he was saying is like more people, and this is not totally obvious, but once you say it, it's obvious. There are more people living like 3.9 miles away from the city center than there are people living 3.1 miles away. Does everyone see that? Because the circles get larger as you go out. Right? They're more square miles. So, what's up? So this is going to be, if we follow the Carlos-Collin method, it's going to be an overestimate of the true population, because we're taking the average population density and we're applying it equally to the entire ring. But people that are closer in the ring have a higher population density, and people that are farther out in the ring have a lower population density. And more people live on the outside of the ring than live on the inside of the ring. Okay, so we're finally getting pretty close to like what we really need to do. Kinga. That's exactly what we're doing. Kinga says, therefore, the way to do this problem is to add up an infinite number of infinitely thin rings. And that is exactly what we do. We take the interval from 3 to 4, we partition the interval from 3 to 4 up into subintervals. Now we're doing real calculus. And we take a particular subinterval between 3 and 4. Now, if we make this partition small enough, then it is correct to say, and also we're going to let n go to infinity, that in that particular ring the population density is constant. Who is following this? All right, let the record show that everyone is shouting in, woo, we get it! Woo! Wait, do you actually get it? Okay. So what we need to do, and this is something we've never done before, integration is not just finding the area under a curve. That's like baby integration. True integration is adding up an infinite number of infinitely small things. And in this case, what we need to add up is the number of people living in an infinitely small ring. Why are we partitioning this up into rings? Because in any given ring, this population density is constant within that ring. Okay? And so if this is like x sub I star, a sample point on the in the ith subinterval, then how many people like live in that ring? Well, how do you get the, if you have population density, how do you get the population? The area multiplied by the density, right? So what is the area? This is not totally obvious, but what is the area of this infinitely thin ring? If this is like, if the width of this ring is delta x, then what's the area of this ring? Yeah, you like imagine this taking this ring and stretching it out, right? If you stretch this ring out, then what do you get? You get this like long thing whose thickness is delta x, and whose length is the circumference of the circle at x sub I out, right? So this is 2 pi x sub I star. I'll start from the beginning again. You take the interval from 3 to 4, you partition up into subintervals. You go to the ith subinterval, you take a sample point x sub I star. Fact that a ring centered at x sub I star is going to have area like the circumference of that circle times the thickness of the partition. Can you nod if you agree with this? Okay, so if 2 pi x sub I star delta x represents the area of the ith ring, and what are we supposed to do with the area of the ith ring? No, we don't. Well, not yet. First, multiply by the population density. Yeah, and what is the population density for people living x sub I star away from the center? P of x sub I star, yeah. Okay, this is like pretty hard, huh? I think. This is the population density, and built into the definition of the population density is that it's constant for a particular distance away from the center. And the units here are people per square mile, and the units actually it's thousands of people per square mile, and the interval and the units here are square miles, and so that's how you know you're like doing it right. Okay, so what we now have is an expression for the number of people living this far away. Now what do we do with that? You now add them up, right? So the answer to this problem should be the sum from I equals 1 to n of P of x sub I star times 2 pi x sub I star delta x. Get it, get it, get it? And finally, what do we want to do to make it like perfect? Take the limit as n goes to infinity. All right, this is like true thinking. So therefore, what should solve this problem? The area of Congressional District A? I think it should be the integral from 3 to 4 of 6 over root 1 plus r times 2 pi r like dr. Right? We sprinkled the magic pixie dust. The delta x became like a dr. Who's following all this? That's like pretty hard, right? This involves like real thinking. The whole moral of the story here is that thinking comes first, and once you know the things you're trying to add up, then you bring integrals into it. Cool? Okay, finish this problem. Does that make sense? And this is a good opportunity to like practice like stuff.
U equals 1 plus r, and you just get like a power plus a power.
Yeah, and then this integral is like not
Kind of
super
like a
hard, but it's like a
problem.
little bit hard. What should we do in a situation like this?
Substitute u for 1 plus r.
Yeah,
You have,
you let
like,
u
two
be
power
1
things.
plus, you let u be 1 plus r, and then, yeah. And then that's like, so then like, yeah, du is just dr. But then we can rewrite this as, well, I'll let you finish, go.
If you substitute u for 1 plus r, then
And then this is good because I can split it up, right?